and we are first going to discuss or rediscuss semester test 1, question 1e. Somebody indicated to me that they are still confused regarding the iterative solution procedure. So first, what we had to realize, just to remind you, we were given inlet conditions of the two reactants, and you were told that the maximum temperature had to be a specific value. So that was specified from this reactor 2. What you were also asked to calculate is volume 1 must be equal to volume 2. The first thing that we must realize is if you do draw an energy balance over this black box system. So you can pretend that whatever happens there, you are not interested. All you know is that your energy balance must satisfy the condition that your maximum temperature cannot be exceeded. Realize that if I draw my energy balance line for the figure, it looks like that, and that maximum temperature, this one, was now specified here. So that was specified. And you can calculate using your energy balance regardless of whether you are operating a 5 CSTRs in series or a single PFR. You could calculate the corresponding X max value using your overall energy balance. So your overall energy balance would still look like whatever was coming into that black box system, FICPI naught, and I am going to heat that up to that maximum temperature from T naught, and I am going to have an epsilon, overall epsilon value times the del H of my reaction. And that overall epsilon value must then be equal to this FA from reactor 2, which is FA naught times 1 minus X2 max. And this X2, that I have here, you must realize this X2 I base on the overall conversion over my reaction scheme. So that is based on that FA naught where it comes into my reactor. So I can then rewrite my epsilon in terms of that parameter. So that is going to be FA naught 1 minus X2 minus FA naught divided by the stoichiometric number of A in that reactor, and that is minus 1. So I've got that in there. My del H reaction was specified. This was given. This was given. So you could calculate FA2 because you knew X max. So that is the first key to solving problem E, is that you realize that I actually know the operating conditions in that second reactor. Right, so let's now, for those who are attending live, please, if you've got questions and you don't want to ask with your voice, I can see comments. I've got my extra screen open here with all be that channel in our Slack workspace. So if you want to type questions, type it there. I will repeat it then and answer as we go along. Right, on a side note. So let's now just analyze the unknowns and equations in our system that we want to solve. So we were asked, volume 1 must be equal to volume 2. This gives me an equation, right? So if I now look at the unknowns here, so let's just collect our unknowns over there. So this is volume 1 and volume 2. Both of them are unknowns. They weren't specified, but at least I have one equation to equate them to each other. What else did I know? I know the mole balance for reactor 1. So for reactor 1, FA naught minus FA naught, and I'm going to write all my mole balances in terms of this blue, the conversion based on the inlet flow rate. So this X1 is now over my first reactor, and I can now say the rate in reactor 1 times the volume 1 must be equal to 0, right? That gives me another equation, right? So if I look at this equation, let's just the unknowns. Unknowns in that equation is X1, and I also do not know my rate. Okay, so can I find an equation for my rate? So let's just now populate here. I've got X1 as an unknown and my rate is an unknown. Do I have an equation for the rate? Yes, I can write my rate in terms of K naught E min E over R temperature 1, and then FA naught 1 minus x1 divided by q. So this is the concentration of A, and FB naught minus FA naught times x1. So that is the divided by q. This is the concentration of B. And we had a whole discussion on, remember to set up your stoichiometric table so that you are able to write this FB. Or FB in terms of x1. So if I now inspect and I want to identify unknowns, I have an additional unknown here into that equation, that is temperature 1. So strictly speaking, CA and CB are also unknowns, but I've already just written them. I've supplied this equation with their function of x1. So you can also list them as separate unknowns. But what I now want to do is I want to say, okay, temperature 1 is an extra unknown that I identified here. Then I can set up an equation that says I can now calculate that volume 1. Volume 1 is equal to, from my mole balance, of course, it's going to be equal to FA naught x1, negative that, divided by my rate. Okay, so there I've got an equation for volume 1. Cool, so let's now go to the second reactor. Let me see if I can get some more space. Yes. So I'm now going to analyze my second reactor. Right? What is important, I am going to start with my mole balance. And now I have for reactor 2. For my mole balance, I have FA into that reactor, which will be FA1 minus x1. And what goes out? FA naught 1 minus x2. Remember, x2 is the blue x2. It's based on that overall conversion over that reactor. And then I've got the rate in the reactor 2 times the volume of reactor 2. So I've got the two unknowns, volume 1 and volume 2. There we go. So is the rate here an unknown? I think about that, and the answer is in fact that it is not. So my rate equation in 2 I can calculate because I know my temperature in reactor 2 is that maximum temperature, and I know the concentration because I know it's associated with that overall conversion 2. And for B, I can also write it based on the inlet conditions. I can have my overall, sorry, that's a minus, almost I make there, let's just clarify that. Small eraser, there we go, negative FA naught X divided by Q. Right, so that is my rate. Let's check for unknowns. Not, this is specified. This was the condition that you have to meet. X2 is, you calculate it using that original calculation for my original overall energy balance. Right, so I already used this energy balance in order to calculate my X2 prior to my trial and error procedure. So therefore, if I make volume 2 now the subject of that equation, I can write it in terms of these 2 molar flow rates. So that is going to be equal to FA naught 1 minus x2 man FA naught 1 man x1. And I do not do, you know, when we use code, you don't have to do all the algebra to neatly write it in terms of x1s and x2s. I can, for instance, have this as an FA1 and this is an FA2, and I have an algebraic equation for these two to make my code appear neater and easier for me to dissect. I'm not sure if you understand what I'm saying. Maybe it goes too fast. I can now, if I have a solver function that I write, okay, let me do that last. Let me show you the solver function last. Let me just erase this for now. Here we go. Right, so, and of course then the min, there we array. Okay, and array is known. It is not an unknown. So the only unknown in that equation is x1. Let's go back to our unknowns list and the equations we have. So the rate, I've got an equation there. Let me just clear up. So I am going to want to solve for these variables. because the rate is actually, rate in 1 is defined as soon as I have an x1 and a temperature 1. So I need 4 independent equations to solve for these 4 variables. So this is certainly an equation. There, I've got my volume 1 is equal to volume 2. I've got my mole balance for reactor 1. So that is my second equation. So I've got equation 2, I've got equation 1. And then I've got in that equation there, where is that? I've got this equation, which is my third equation, the mole balance for reactor 2. So I've got 4 unknowns. I need 1 more equation. And that, of course, is to solve temperature 1 from my energy balance, over reactor 1. So I'm just going to copy and paste, but I don't know how to do that, so I'm just going to write it out. The energy balance for a CSTR, temperature 1 minus temperature 0, plus the epsilon value over reactor 1 times the del H of my reaction. Must be equal to 0 because that reactor must operate adiabatically. And this, of course, I can write in terms of the molar flow rates from my reactor and into my reactor and the stoichiometric number. There we go. So once this is of course now my 4th equation. So I've set up the equations, enough equations, yes, I've met my goal, good join. I've got 4 equations to solve for these 4 unknowns simultaneously. And of course, if you employ a solver, you can actually just write all 4 these equations with residual values. In other words, set all of them equal to 0 so that you can solve. But easier, and then what the implication is if you set it up like that, so if your solver function returns equation 1, equation 2, equation 3, and equation 4, it means that you will have to have 4 corresponding guess values for volume 1, volume 2, x1, and temperature 1. And that makes it a very user-unfriendly problem to solve. Right, so we would rather set up our equations in terms of a convenient variable. So this is where problem-solving skills comes in, to realize that as soon as I guess a value for x1, let's just go through our equations. As soon as I guess a value for x1, I can solve temperature 1. And once I have solved, so I guess a value. Picture you've done this many moons ago when you did search and you had to use a trial and error or a fixed point iteration protocol in order to solve that. So you will guess x1, right? Once I've guessed x1, I can solve, so this is my procedure. I can solve temperature 1 from equation 4. So I can solve temperature 1. Then I can solve rate in reactor 1, and I can solve volume of reactor 1. Okay, so let's just make sure that I can do that. x1, I've got the temperature. I needed the temperature to calculate my rate. I can solve the volume from that from that guessed value for x1, because everything is now known. So now I must see what happens to my other equations. In order to calculate volume 2, the only variable I needed was x1, which is guessed, so I can already calculate volume 2. And what is my final test then? My final test, so once I have that, I can also use the mole balance for reaction 2 to solve for volume 2. Okay, and my test then is, have you achieved success? Is to say volume 2 minus volume 1 must be equal to 0. Volume 2 minus volume 1 must be equal to 0. So we can then use that as the function that we return. So in my solver, if I now have fsolve that I want to solve, the function that I will define will only be a function of x1. So for my guessed x1, I can calculate temperature 1, I can calculate FA1, I can calculate my rate, or FB1, I can calculate rate 1, I can then calculate volume 1, and I can calculate volume 2. And I only return my residual function, res equal volume 2 minus volume 1. And this is the variable that you therefore guess for in order to solve these two volumes. So once you now have your solution, after you run your if solve, so if you achieved success, I found the correct x1, you just apply this whole procedure, tick, tick, tick. So you copy and paste, copy and paste for your answer in order to solve for those two volumes. So you can then just check, am I in fact correct in my code? Right, so I haven't seen anything in Ask Elizabeth. Can you just maybe just indicate to me? So I'm going to stop the recording, so I'm coming back to Blackboard screen. So just